So I'm very pleased to have as our speaker Thomas Edgar, who's Professor of Chemical Engineering and the Able Chair of Engineering at the University of Texas at Austin. He received his PhD from Princeton University, and he's had a very wide level of professional service throughout his career, including president of A Squared C Squared. He's done research for quite a few companies, most heavily in the microelectronics field in the last 15 or 20 years. And that includes Advanced Micro Devices, Motorola, Texas Instruments, and the Semitech Microelectronics Consortium. And he has a long list of honors. And to give him time to speak, what we'll just mention is that that includes the election to the National Academy of Engineering. And I look forward to, and I'm sure all of us look forward to hearing his talk. And let's give him a warm welcome.
Okay, well, thanks, Richard. You know, the title of the talk says New Directions, and we are going to talk about new directions along the way, but I think it's important for people to understand, you know, about the past and where things have gone and why we've gotten to where we are today. So we'll be engaging in a little bit of a historical review and not too much revisionist history along the way, hopefully. So here's the outline of the talk. We're going to, again, try to help set the background and stage, since many of you may not be involved in this field. In fact, I would say that the number of really hardcore control and modeling people who are in this field is really less than 10 in terms of people who might be at this meeting. So I assume that many of you are here to sort of understand what this field is about and where it's maybe heading in the future. You know, equipment control is paramount, and we'll talk about the nature of control and the kind of processes that are used today in semiconductor manufacturing, and especially because it's a batch process, and that makes it have some rather unusual characteristics. We'll talk also about why APC has been readily accepted by the semiconductor industry and what value it brings. Then we'll get into a number of different examples of, you know, where essentially advanced control is applied. And I should also mention that I use the word APC, and some people, APC stands for automatic process control. In the semiconductor industry, they think all control is advanced, so they say advanced process control. But in any event, we'll talk about controller performance monitoring. And then the other part of, I think, this area that makes it somewhat unique from a control perspective is the idea of factory control, where you've got lots of pieces of equipment. It is a very highly complex set of operations that go on there, and control is part of that, but like I said, control faces a lot of adversities. And then at the end, we'll talk about some new directions as well. So here's some history that gives you an idea about how APC came into the semiconductor industry. Probably one of the signal events that occurred back in the 80s was the formation of an organization called Semitech, which was really founded to combat the semiconductor activities, especially in Japan. And so how can the U.S. compete? And so they viewed this as a defense imperative that, you know, we need to be able to support this industry, so don't rely on foreign suppliers for chips for our defense industry. So they put a bunch of money into it. They said only U.S. companies can be involved. And they actually started on this idea of technology roadmaps, which is, I think, a rather you know, unusual part of what makes this industry rather interesting. It didn't seem like they worried too much about control of equipment. You know, you would basically buy equipment from a vendor, install it in your plant, hope it works. And of course, you know, they had their own software in there, their own ways of hooking up to you know, the rest of the process. In fact, some of the equipment may have been built in garages in Southern California, for all I know. So it was really, you know, lots of different suppliers and vendors. But then we started seeing some order out of the chaos, and they started having workshops on advanced equipment control. How do we do a better job of controlling the various unit operations that are in semiconductor manufacturing, et cetera. Then the wind kind of went out of the, you know, protect the national industry in 96. It became an international organization, so companies from outside the U.S. were welcomed in. And so then they expanded the roadmap activity to include those companies, and that's called the ITRS. And then most recently, Semitech moved to New York out of Austin, Texas. Many of us in Texas were sad to see it go. You can see there I say end of life. Well, unfortunately what's happening is that a lot of those mainstay companies like Samsung and Intel have now just in the last few months bailed out of Semitech. And so it's very unclear where things are headed right now with that organization. In fact, someone said, yeah, we're now looking at IMEC in Europe as the way we're going to get things done. So unclear where this is going to go, but we still have these conferences that are held around the world called AEC, APC, Advanced Equipment Control, Advanced Process Control. And so you see here essentially 3 different conferences that developed over time. The original one is down there at the bottom. The one that's held, in this case in Austin, but it's held in the U.S. And that's now, as you count, if you do the Roman numerals there, it's the 27th one, okay? So they've been doing this now since 1998, so that's pretty impressive. Along the way, Asia decided they need to have their own conference. You see the APC, AEC, APC Asia, and then Europe has its own one, and they've done 15 of them. So there is a lot of activity around this whole topic. And again, I'm not going to ask for a show of hands as to how many people have ever been to one of these conferences, but they are, you know, they have their own little communities that operate. I mentioned roadmaps. So here's been the thing that's been so impressive, I think, about the whole semiconductor operation and Semitech especially, is that they basically, and this is a roadmap from 2004, so you can get an idea about where they think they are and where they're headed. And if you just look at one of the lines there, you see how, you know, the nanometers there, they keep pushing down the size to very small size, i.e. nanometers. And so what they're doing is really driving what the devices are going to look like in the future. And what the devices are going to look like in the future is they're going to be smaller. So we all know this ourselves because, you know, we buy smartphones, we buy other things, and everything has gotten much more compact, et cetera, hopefully using less energy as well. And a lot of this has become, the companies come together, they get their experts, they figure out where things are headed, and then they figure out what are the technologies that need to be implemented in order to get there. And in the end, it's really the consumer that's benefit, and it's really the consumer who's driving this whole thing because, you know, we want smaller devices, and so and we're willing to pay for them, and so the companies then compete, you know, about who has the best phone or the best other kind of, you know, best laptop, et cetera. So this is again something you don't see in other industries, and it's a very interesting characteristic. But again, as you can see, we're pushing things down to, you know, very small scale, and that again is one of the challenges of doing semiconductor manufacturing. This is the other part that you have to understand about a fab, is that it's a whole sequence of unit operations. I've just listed some representative ones here involving chemical vapor deposition, ion implantation, oxidation. You get another CVD round. You do masks to essentially create a surface where you can carry out etching and other activities, and so on. So it's really, here you see, you know, maybe 10 different unit operations. Well, actually, in some fabs, you have up to several thousand process steps as they build up these layers of material, and that might involve 200 unique processes. And so, again, the complexity of what's going on here is just staggering, and it's a wonder that they can actually make the devices that they intend to make. It's also helpful to understand, you know, how this may be different from, since so many people may, you know, be more familiar with process control, and in the continuous industry, you've got refining and chemicals. And, you know, we have different objectives in the semiconductor industry. I mean, first of all, it's largely batch and discrete rather than continuous. Your primary objective is to end up with a device that has the right electrical properties, but then you're going to try to control things like line width and critical dimension. And then for economics, you're trying to maximize yield and minimize cycle time so you can essentially make the largest number of good chips and as fast as possible, so you essentially use the equipment that you have there most effectively. The other problem is that once you make something, it's hard to unmake it, okay, or rework it. In other words, in refining and chemical industry, they have lots of these things called storage tanks where they can say, oh, well, we missed the target on this one, let's blend it with something else. Well, so that's a luxury that you don't have in the semiconductor industry. And, you know, there's lots of measurements. In fact, there's no data famine that seems to be appearing here. There's plenty of data being produced. So when you look at the different unit operations, and we'll talk about a few of them specifically, you know, what's their characteristics? Well, they're very physically and chemically complex. They are, you know, in the end, either physical or chemical processes. There's a lot of things we can't measure. In fact, very rarely can we measure what's going on in the middle of one of these unit operations. We have to wait till the end of the unit operation. Very sensitive to process changes, nonlinear processes. They all tend to be multiple input, multiple output. And the other thing is that, you know, the people who design the chips are not the people who operate the plants. So as a result, you know, there's sometimes a mismatch. Someone says, oh yeah, this will be a great chip that we can have certain characteristics, and then the guys in manufacturing can't figure out how to make it, so, or operate successfully. So those are some of the challenges you face. And this just gives you an idea of all the different things going on in a series of unit operations that could be applied to make a final product and pattern transfer. You can see a list of all the different variables. I don't intend to really talk about any of them in particular here, but again, it's a very complex multivariable process that requires a lot of attention to details. And this gives you an idea about time scales in a typical fab. I mean, we've got some things happening in real time, you know, less than a second, but you can do fault detection, and that can be done over longer periods of time. We have something called run-to-run control, RtR. You'll hear more about that later. That can be spanning over minutes to weeks even. So again, you know, you can actually have from the time a wafer goes into a fab until finally, when the bare wafer goes in, it might be 6 weeks before that product actually comes out after it goes through all the steps. So it's a very, again, from a scheduling standpoint and operation standpoint, it's very complex. And we can worry about other things like, you know, do we control each wafer? Do we have a bunch of wafers and try to control representative wafers that we can sample? But again, the big challenge is it's hard to get data in the middle of the operation. You almost have to wait most of the time till the end. So again, if you go back and think about this as in a general batch processing hierarchy, they have all the things that you would have in a batch chemical process. I want to highlight here steps 3 and 4, which is one called within the batch control, which means that we actually try to control what's happening during the run. And then finally, the mainstay of semiconductor process control is really run-to-run control in order to meet the quality constraints. And again, we'll get into that in more detail. So again, some of the characteristics, you know, we have to satisfy the final product quality at each step along the way. And, you know, if you do the math on, if you're going to have 200 sequential steps and you're going to have 99% yield at each step, and then you multiply those out, 9.99 to the 200th power, you end up with a fairly low yield overall. And so that's the challenge. Every step has to be done very well. The other problem is that because you have a different industry that provides the tools, plasma etching, CVD, et cetera, to the manufacturers, then they have to figure out how they combine those pieces of equipment with the way they operate their fab. And the problem is you usually can't modify what the hardware and software and the tool is, and that creates big problems. And so that, again, is another driver for why people have gone to run control. The other part of this is that it's very complicated operations that can involve both chemical steps and also mechanical steps. And a couple of examples will be lithography, CMP, chemical mechanical polishing, or planarization. And this just gives you an idea. Again, there's not much going on here, but just that they have these tools, they have robotics to bring the wafer in, they operate on it, and then the robotics take the wafer out, again, under a very highly controlled environment because they can't have particulate matter in there. It used to be that, you know, you have these gigantic fabs and lots of people running around what we call bunny suits, and you had to control particulate matter, and it was just a very difficult situation. So the industry's gone more towards, you know, let's control what goes on in the tool, have a lot fewer people operating, And in fact, let's move everything around with robotics instead of having people moving these things around, and that's been largely implemented in the big fabs today. Some other things we can do with batch processing that makes it a little bit different is that sometimes when things aren't going well in the batch, we actually can adjust the amount of time you use for a certain process. Like, you can decide, well, I'm going to etch this one maybe a little longer this time. So, we can take advantage of the fact that this is a batch process. Again, there's lots of challenges within the batch control. I'm going to talk about a couple of examples of where this is actually useful. Again, the whole problem of modeling it, nonlinear behavior. We don't have sensors that are going to do the job we need during the batch, et cetera. Lots of disturbances, behavior that's irreversible. And, in the 90s, basically we had multi-wafer reactors that we carried a lot of the steps out on. This is the top plot there is a LPCVD, low pressure chemical vapor deposition reactor. They would put anywhere from 50 to 200 wafers in there, and then basically essentially deposit silicon, polysilicon, for example, on the wafers. And this worked pretty well as long as you had only 4-inch wafers. Once they went to 6-inch wafers, they started finding that the uniformity of the wafer was becoming a problem because of the nature of the heat transfer in the furnace. And so gradually the industry moved towards single wafer control so they could actually do a much better job of controlling what happened on an individual wafer. And the wafer size has actually grown over time. Later after they had 4-inch wafers, they went to 6-inch wafers, then 8-inch, then 12-inch, which is currently pretty much the max size, although interestingly enough, there are lots of 8-inch fabs out there and processing units that people use. They can make a profitable product, and as someone said, they've all been depreciated, so they actually have a low cost of ownership as well. But basically, this is a way in which we get much better control of what happens on the wafer. There's talk about going to 18-inch wafers or 450 millimeter wafers. That one is unclear. I couldn't get, when I talked to people in the industry about whether they really think that's going to happen, it's a very expensive proposition to talk about now all of a sudden changing your whole fab to a new generation of equipment. So again, there's some big economic barriers to doing that. So here's an example of what you try to do. If you're going to now take those 200 wafers you used to run all at one time for an hour and a half, now we're going to try to speed it up, because the point is I can't take a long time to run each wafer one at a time. I've got to try to speed it up by running at higher temperature, and so we do what's called rapid thermal processing. And this is something that's familiar to most of you in the room about, we have a set point trajectory. We like to be able to follow it. And we have this black area there called the bring-in area that essentially, our goal is to minimize that. So we like to track the set point as closely as possible. You might say, well, yeah, but why don't you just overshoot it? Well, if you overshoot, then you start damaging the material, and it doesn't turn out to be high quality. So we've got to actually bring it in as fast as possible with as little overshoot as possible. So here would be a typical RTP reactor that's got these lamps that are radiating heat on the reactor. You can kind of see in the picture here, there's some maybe concentric zones of lamps there. And so, here would be a system that we actually worked with at Texas Instruments, where you can see we've got like 4 zones that we can independently control the heating from. And then we've got a wafer down there. In this case, we actually had thermocouples that we mounted in the wafer. Of course, you can't do that for actual practical operation. But again, in the early days, we were trying to show that, well, we really need multivariable control in order to successfully control a reactor like this. And in fact, and this was part of a DoD program in the early days of semiconductor manufacturing, 1993. And the student I worked with basically developed a nonlinear heat transfer driven model, and because it's radiation, you have T to the 4th terms in there, so clearly nonlinearity is at work there. And we like to be able to control this thing in real time over a space of 10, 20 seconds. So having used some of the ideas of model predictive control, or DMC, formulated as a successive linearization type of problem, And then here are the results we got. You can see that, if we're trying to ramp this system up from 400 up to 800 degrees C, you can see that we do a pretty good job of being able to get all 4 of these thermocouples to track the desired profile. Again, a little slower than maybe we wanted, but anyway, we were able to show you could do it and do it in real time because, the computer is basically cranking out new models as you go along, as you get up to the higher temperatures. So this is an example of what you could do, and again, this is a sort of approach that's used today. There's a lot of examples of model predictive control that have been used in the semiconductor industry, and I'll say more about that later. Here's another system that essentially lended itself to model predictive control. This is CMP, chemical mechanical polishing, where you've got these arms that basically push down on a polishing pad that sits on top of the wafer, and this is a way, again, of reducing, instead of etching, we actually polish the wafer down, depending on the material we're trying to remove. This turns out to be, with the 5 arms, to be a multivariable control problem as well, and we have to worry about adjusting each of these arms. The arms are rotating around as well, so it's, again, a very complex mechanical process. And we did basically, the student Jarrett Campbell, who was at AMD, part-time and part-time at UT, basically said, hey, he had learned about model predictive control in classes, and he said, let's just figure out how we can apply it to this problem, and so it turned out to lend itself really well. And I think, having scoured the patent literature, this was probably the first application of model predictive control in the semiconductor industry on an actual commercial tool. So again, we worry about, how we do this at the tool level. We're now going to talk about things like run-to-run control, that's part of what you see here. We also have fault detection we have to worry about. I'm not going to talk much about fault detection in this lecture just because of lack of time, but there certainly are lots of opportunities to look at that. Again, variation is the name of the game here. Things are changing all the time. We've got tools that behave differently. We have different lots, and they get exposed to different tools at different points in time. Chambers change over time. You have what's called seasoning of a chamber, that after a while the chamber operates consistently for a while, but then you start getting deposits internally, and then it doesn't operate quite the same. So keeping track of all this is very hard to do. I have to decide when I'm going to shut down the system. That's expensive to do, and so on. So those are some of the things we worry about. So I mentioned run-to-run control. We'll go through this again. There's a few equations in here that we can talk about. The whole idea is because we can't measure during the batch. It's hard to do. That previous example I gave you, we actually had to put thermocouples on the wafer. Well, that's not feasible in an actual operation. So, we're pretty much stuck with saying let's measure it at the end of the run and essentially adjust after every run what we're doing with the process. And so it does set up nicely as a discrete time process, and it is good for handling the kinds of variations and problems we run into, and we can do run-to-run optimization as well. And so this is basically the sort of model predictive control or internal model control viewpoint. We've got a controller which tends to be real simple, deadbeat controller, or we can use MPC, EWMA. The process is going to be fairly simplified. I'll show you a typical model that they use for run-to-run control. And then we have an observer that basically has to filter the noise out of the system and other things that are changing as well. And so people typically use exponential filters or Kalman filtering. So here's a standard thing. You might look at this and laugh, say, well, that's so simple, even a caveman can do it, and that's right. But again, with all the other things changing in the fab, you actually don't want to have another complexity added to it. So this has been extremely successful. I'm going to show you some results that were obtained just by using run-to-run control. But basically, you're saying that the model is really simple. It's linear. Essentially at the end of the batch, you're going to compare the measurement C against the target, and then calculate a deadbeat controller. And then we filter the state update. And then when you wrap all this together, then you basically have an integral controller. So we're familiar with PID controllers and certainly the process control world. This is essentially an even simpler case. But again, it's applied on a run-to-run basis. So here's one of the early results actually at AMD, where they said, okay, we've gone from essentially manual operator control, and now we're going to use run-to-run control. That's going to be now automated. The operator doesn't get to touch anything along the way. And so you see some of the results that they got in terms of improving the performance relative to the target. You can see the numbers there, big improvements, 70% change in terms of being closer to the target. And then, of course, the whole goal is to narrow the distribution as well and improve the CPK or process capability. So all these things came out of one of these early studies on run-to-run control, and everyone started latching onto it, saying, okay, yeah, this is a way in which we can do things like increase yield. That's going to improve our economics. We'll be able to reduce the amount of scrap that we make because, again, those are lost products and you can't sell those. We'll be able to run the equipment more often and have a higher yield in terms of good wafers, and then maybe run faster and reduce the cycle time. So those are all things that affect the economics. And of course, in a typical fab, you've got a lot of interesting things going on in terms of when are you actually making good wafers. You know, how often are you really sending through pilot wafers to try out a piece of equipment after it's been shut down? That's a cost, of course. You've got scheduled downtime and unscheduled downtime, and then sometime is idle. So, you know, again, the cost of ownership issue is always with you, and when you've got a fab that costs anywhere from $2 billion to $4 billion, then people pay a lot of attention to how much the equipment is getting utilized. Here's a good example that shows you, how, again, why going to something like run-to-run control was effective in terms of improving CD control on the gate. And as you see the plot there, you see the one with the wider distribution was essentially one that before they actually implemented improved control. And the narrow distribution is the one that's closer to where we want to be. We also avoid some of the bad areas of where we have a bad device. But also, as we move that curve to the left and don't move it too far, we get higher speed devices. I don't know if some of you remember when you're looking at what prices of computers were back 10, 15 years ago, you would see different megahertz ratings, and of course the ones that are slower, you didn't have to pay so much for, and you could buy, more expensive ones if you wanted to have a faster one. And so, in a sense, this is really the economic proposition that if I can make faster devices, I can sell them for more money, and my profitability goes up. So here are just a couple of numbers about what happened in the case I just said, that they were able to increase the speed by 8%, reduce the variability, and they greatly reduced the amount of bad chips that they had to rework. And when you translate that into, what does that mean in terms of savings or in terms of increased profit? And this is like the capacity argument. If I can increase the capacity, then I can essentially make a lot more money because I can take all those chips that were bad before, now they're good, and then sell them. And in a competitive business, when AMD was fighting against Intel, that was one of their standard competitors. Then when they had an improvement, then they could sell a whole lot of chips. And so this made a big argument. $240 million a year is a fairly powerful argument for why you need a bunch of people doing APC. And so that argument was actually successfully used at AMD. They hired a whole lot of, in fact, PhD students from my group and other groups. So that was a good thing that happened. Now let me shift gears and talk about some other processes that are of interest. I mentioned plasma etching earlier. This slide is really to indicate to you that it's a very complex process. There are very few physicochemical models that seem to work in a plasma system. There's so many parameters you don't know, and so having a first principles model here has been essentially an ephemeral goal that no one has really been successful going that way. But we do have lots of measurements from a plasma etching system. We've got a number of things we want to control. Those are the performance variables. We have a number of manipulated variables that we can adjust in order to get the performance variables to where we want them. But then we have lots of disturbances, and you see all the ones that are listed there. Lots of things going on. And we also have a ton of measurements. And so here you get an idea. This was actually some work we did with Samsung, that we could have as many as 1,300 different sensors or data points on a plasma etcher. And the question is, okay, so how do I take those measurements and then translate them into manipulated variable actions. And so sensor selection algorithms is essentially paramount. I think we've got a lot of work to do on that one. You know, that's not a problem that's really been, I think, well solved yet. So here's another example. It's the resist etch process, and the whole idea here is that again, as we try to go to smaller and smaller dimensions, and you know, you lay down essentially a resist that essentially was maybe wider than you want it to be, and so they figured out that, well, we can actually use etching to trim that resist. And so you see in the diagram there, you know, how we might want to reduce it from, say, 65 nanometers to 40 nanometers. And so we're going to do that chemically by using etch. And so I'm going to essentially talk to you about some work we did with Tokyo Electron and IBM, where they were trying to do wafer-to-wafer control. You know, you were essentially faced with, okay, we have to measure information about the wafer coming in. And if you notice that they're saying, the slide here says FF, which stands for feed forward. So typically in the industry, they kind of viewed things coming in as being the feed forward information that you could operate on, maybe using feed forward control. And then the measurements we got at the end of the batch is something we would use for feedback control. But of course, we have to be able to measure things. And in fact, in this case, scatterometry, which is fairly expensive, was used as a way of measuring some of the variables. So this project, again, was to look at interactions between lithography and etch. And it wasn't just worrying about critical dimension, CD, but also what does the sidewall angle look like? And you'll see some diagrams of that in a minute. And then finally, you know, what's the uniformity on a large wafer? Are we able to get, for every device that we're going to make on a wafer, you know, a consistent result? So those are the challenges. And again, it sets up very nicely as a multivariable control problem. Here again, you see a cartoon of what things look like. We've got the photoresist there in yellow, and we've got, you see where the CD that we're going to be measuring, and you know, we're going to be etching that down to the CD after the processing on the right side there. And again, we're going to measure pre and post using scatterometry. And again, the parameters we want to be able to measure are CD and sidewall angle. So again, adding the sidewall angle, which was found to have a significant effect on the performance of the chip, was essentially a new part of this. And of course, the other problem is, you know, how do we model the system? So we have to understand, you know, what the interactions are between the different variables. So here again, you see again how the profile is going to transfer onto this polysilicon. And then we're going to try to understand, you know, exactly how all the different variables are related. So, so it's a chemical process. You can see again, you know, we've got lots of little, you know, cartoons here about what the different chemistry is involved. We did not try to model the chemistry because, again, that became a fairly impossible problem that really couldn't be implemented in a manufacturing environment. And so we said, okay, let's just try to understand what the control knobs are, the manipulated variables, and we'll figure out, okay, what the control variable is going to be. And again, depending on whether it's the resist etch or the polysilicon etch, we had different variable relationships that may be operated there and perhaps different manipulated variables. One of the purposes of this study was to really figure out what are the best manipulated variables to use in what was essentially a non-square system. Again, the idea, let's stick with the simple models, use design of experiments, develop some nonlinear models, and then wrap that into some sort of run-to-run control framework. So again, it's a multivariable control problem that we can use quadratic optimization on or with constraints that we have to worry about. So here you just see some of the results that one gets, which we did as part of the study. You can see the blue dots there are what we achieve for a consistent sidewall angle. The red lines are the ones where we said, let's just control for CD and just see where the sidewall angle ends up. And you can see that the performance is not nearly as good for the red X's that you see in the plot. So percent improvement, about 80%. So that was really, I think, a great result. The CD delta is, again, getting the difference between the CD on two spots on the wafer, one near the center of the wafer, one at the edge of the wafer. And again, you can see with MIMO control, we can do a lot better job of staying close to the target. And again, the red X's are, where we don't control for that, and you can see it works very poorly. So again, this is, again, demonstrates the value of APC. And then the summary table here is just to show you some of the percentage improvements, but again, quite significant, quite motivating. We basically worked on this project and then it was handed back to the vendor and IBM, who then didn't tell us what they did after that point, but it was clear that they were going to work on it. So another part of this is, with all these run-to-run control loops, how do we know how well they're doing? And so we basically did a controller performance monitoring project with Texas Instruments to look at what happens. The term high-mix fab, by the way, refers to a fab where you're running lots of different products as well as lots of different tools. And so if you see that second bullet there, a typical control engineer in the fab, just for this one unit operation and keeping track of different layers where you're going to do something different at every layer. You've got different products, and you're going to try to track all these different things. They all have a different control protocol they follow, and when you do the multiplication, potentially this person is worrying about 800,000 SISO loops. So very challenging from a dimensionality standpoint, and so we actually had done some work on performance monitoring of PID controllers, and we said, well, hey, integral control, we should be able to come up with something simple here, and so we did that. This is just to give you an idea about a few equations that are involved. The whole idea is that zeta is essentially a measure of how well you're doing. The closer you are to 1, the better you are to optimal performance, which would be essentially minimum variance. And if you're off of less than 1, that means you're not performing as well. So here you see an idea of what happened over a period of time in terms of performance variation with essentially a particular piece of equipment. You can see that the blue line is really just it's kind of a curve fit of the whole thing. So you can see that there are dips that occur, but then toward the end of the data there, you can see it's starting to drop off. So that indicates that, okay, the performance isn't doing too well. And in fact, here's a distribution. You can see that we were above 0.8 for most of the time, but you can see there were isolated cases where the performance of the controller went way down, where again, if you're an APC engineer, this is the kind of information you'd like to have sent to you automatically through an email saying, okay, here are the loops you need to pay attention to, and they can address those, because they can't pay attention to the hundreds of thousands of other things that are going on that seem to be working okay. And so there's a lot of things you could do here in performance monitoring. I mentioned a few of them. One of the problems is that when you think something is going bad, how quickly can you operate on or can change things? And so that is actually a big challenge. We worked on it for a while. We weren't able to get down to the, oh yeah, you can find this out in 2 or 3 wafers level. It's more like 10, 15, or 20. So that's a challenge to figure out how to do that given the nature of the data you have. So let's now move on to talk about factory control, because again, this is actually an Intel fab, by the way. That's the other rather unique part of APC and semiconductor fabs that we have to pay attention to. So the notion of fab-wide control came up, roughly about 10 years ago, and how are all these different unit operations going to work together? And we have islands of control that are basically different pieces of the process, but then we still have to worry about what happens on the overall fab. And this is just another picture, in this case AMD, where you can see again the whole sequence of operations and how we take a wafer and we go from one unit operation, then we do a measurement of that, and then we have a controller that basically does a run-to-run operation. And then the metrology there is, again, a peculiar term that is essentially used in the semiconductor industry that basically stands for measurement. But there's a whole industry built up around metrology because it's fairly complex. People sell separate pieces of measurement equipment. They don't always come with the tool. And so that was part of what needed to be done here. So again, putting this all together, very challenging. But again, companies like AMD were very successful in doing it. And by the way, AMD is now called Global Foundries because they split up the company about 4 or 5 years ago. So if you think about, this complex set of unit operations, as long as we think about APC, we know kind of everything is going on. We're not going to change anything on the fly. We're not changing the recipes. There's no equipment maintenance that takes a piece of equipment out of service. Then we can sort of lay this all out, solve an OR problem, and figure out how it's going to be done. But the problem is in a real world, in the real fab, you got lots of things going on. You got reworks. You have some equipment that isn't available. You got equipment in parallel, multiple pieces of equipment that have different behaviors, and you don't know which piece of equipment your wafer is going to go through. And so how do you adjust to that? And so on. You've got, people running pilot wafers, et cetera, engineering lots. And so the process flows might start off this way, looking fairly simple, but then again, as things start happening in the fab and you have, multiple pieces of equipment and, scheduling things, you're making different products, then the process flows become very complex. And so this idea of a multi-product, multi-tool processing facility came into vogue again in the 2000 era. And the problem is, of course, we're trying to keep track of, okay, multi-product, we're making more than one product, but we have one process. Well, that's a fairly easy problem to solve. And if I have a single product and, say, two processes, then I can figure out how to do that. But when I've got multi-product, multi-process, then things become very complicated. So this just gives you an idea again of, it is important to track what happens in each tool and which product you're making. And so this just gives you an idea, the animation of, tool 1 may make A and B, but then it makes tool 2 is used, make 5 and 6. And so again, notice that, if you decide you're going to measure all these things sort of serially, then basically you have to keep track of what's happening and what the history is of each wafer. So this idea of mixing and matching, that you've got different pieces of equipment, different products, and what is the right, which tool do I want to use, what's the best one. But things happen along the way, tools change. There's this idea of control threads that was introduced in the early 2000s that, let's really keep track of the path that the wafer takes and really try to understand what each piece of equipment is doing along the way. And so that's called the context, which is, the conditions in which it's operating and what variables are essentially worrying about. So this was essentially an idea that was tried early on because of all the sources of variation. And if again, without defining threads, then you lumped all this data together. And so here you see a plot of essentially if you were watching all these different wafers coming out from different tools, then you look at a plot like this and you say, well, hey, this process is not in control, okay, because things are going all over the place. And so this is two tools and two products, so a real simple simulation. But then if we say, okay, let's try to understand, the history of each product, which tool was involved, and we can actually essentially say, okay, there really are four combinations here that are important, tool 1, product 1, tool 1, product 2, et cetera. And so now if we start looking at the data and segregate it, then you see something like this, where now, okay, now things are making a lot more sense. I can now track what's going on. And again, in the beginnings, people didn't really realize that. They just said, okay, we just lump all this stuff together, and we don't really have any way of essentially clearing up the data. And so this was an example of how it was demonstrated in an actual fab. Without threads, there are going to be the white boxes, empty boxes, and the dark boxes. Using threads, and it's pretty clear that threads was a lot better approach. But one of the problems, and again, this was used in overlay and line width, that we had to basically worry about lots of variation in overlay. And here you see, and this is a very complex system where you're trying to actually create the image. And so you can see all the things that can be going on in overlay. That's a problem for us. And it's a very complex process where you have essentially markers on each level where you're actually trying to figure out, okay, where is the wafer position? How is the one layer positioned relative to another layer? And you can see, they worry about translation, magnification, rotation. So lots of things can happen in this mechanical movement of the wafer. And, how do we keep track of all this? So again, complexity, rules again. But again, we figured out with actually it's a student named Bodie, is not related to the famous Bodie, by the way, but we'll let that go for now. But in this case, they were trying to control 8 different overlay parameters or variables, and you see them listed there. And so again, very complex process, but again, one that set itself up very well for LMPC. And in fact, I should mention that this paper actually won the IFAC Control Engineering Prize back in the early 2000s. Okay, so metrology variations, as I showed you, you're not sure what order things are going on. If you're not careful about how you track things, you could basically take the data on the left and then reorder it, and the trends you're going to get from that are going to be totally different than what you expect. So asynchronous feedback became a big problem, taking things out of order. And the problem is that, sometimes, stuff happens in a fab, so you have to do things out of order. You have to keep track of the data, and it's very challenging. So one of the things that we discovered, though, is that, the other problem with threads is if you had too many threads and too many variables, then the number of threads you had to keep track of became just astronomical, the so-called, curse of dimensionality. And so we worked on the idea of, well, let's try to keep track of what each tool is doing as it goes along with each wafer or each product, and then see if we can take all that information, combine it together, and using tools of estimation control, figure out, let's take the data, analyze it, and mine the data, and figure out what's going on instead of doing the thread approach, because that was going to become hard to do as we went to more and more products. So again, using some sort of recursive least squares approach, you can actually do this. Again, because we have a simple model. The model at the bottom there is really to give you an idea of, we've got these different steps along the way, and if we track them, we know essentially, if we get data at the end that's kind of a summary or essentially a conglomeration of all the previous errors that are in the process, then we can go back and deconvolute that data and try to figure out what the individual errors are. And so again, the control law is real simple, the deadbeat control law, and the notion is that you're going to try to solve essentially a non-square problem, a set of equations where you got more equations than unknowns, and then solve that problem. It's also an ill-conditioned matrix, and that's a problem as well. The A's, by the way, I'm not going to get into the details, are all ones and zeros, so that makes it kind of an interesting mathematical construct. We have a weighting matrix that tries to introduce a filtering kind of effect, and it's a lot like, again, the linear quadratic problem. And then we did some simulations just to give you an idea of how well it worked. Let me just skip ahead here. So this is actually a step change in a state. That's the blue line. The red line is what happens if we use threads and EWMA. You can see we get when the disturbance happens, and there's lots of things happening as we go to different lots here. Different other disturbances come in. The EWMA, because it's actually based on a thread, well, if that thread hasn't had a lot of data points lately, then it's not going to give us current information. Whereas the JADE approach, not the jaded approach, but the JADE approach, basically stayed right on the target very well by, again, combining all the information. And here's just another example of, as you're tracking the parameters and what happens with, the estimates of the parameters. And so you can see how they kind of ramp in, over time, which is, again, kind of expected behavior for the parameters. And this is the part about the threads, about if we have a lot of different products and tools, how many threads do we have? You can see that it doesn't take long to get up to like 400 threads. So from a practical standpoint, it's really hard to work with the threads. And again, this just compares the EWMA standard approach versus the JADE approach. And again, the mean squared error is a lot better. There was some work done by one of my colleagues, Jin Wong, at Auburn, on looking at the singular regressor matrix, and also the whole issue around poor input excitation. You're sort of relying on the normal plant operation to give you enough data information that you can actually do the fitting. So having input excitation, and in fact some people suggested is that you ought to keep track of this and actually decide to use a tool where that you haven't run in a while, so you can get up-to-date information. And so again, simulation work that we've done with Jen essentially looked at a number of things like covariance resetting, Kalman filtering, EFRA, which is a forgetting factor approach. Again, the JADE approach seemed to work pretty well. Disturbance detection is still the issue with that. So I mentioned fault detection. Again, there's a growing amount of activity here. I'm not going to talk about it, but again, the framework of fault detection fits in pretty well. So again, track the health of a piece of equipment, as you see here. So the last part of the talk, I want to talk about development of shapes, because that's kind of looking down the future. You could say this is nano manufacturing, but really the people who do semiconductor manufacturing today are really doing nano manufacturing. But this is really a slightly different approach. The whole problem as we move to these smaller dimensions are going to be the exposure systems or the steppers. And, there has to be, again, the ability to get enough energy in order to create the image you want. And that means that as we go to smaller dimensions, we need bigger and bigger systems, larger in scale, and more power in order to do that. Someone suggested that this is where we're headed for the next lithography device. And, and when you do the math, do the economics, you can see kind of where we are here as we go up the 2010. And everyone keeps holding out essentially enhanced or extended UV is the way it's going to go, but there is still no product on the market, and they do all kinds of workarounds using quadruple patterning and all kinds of other things in order to make the current system work. But at some point it's going to break down, and we're going to need to go some other way. A number of my colleagues at Texas say we should be using imprint lithography, and so they're working on this idea. The whole idea is it's like a printing press. You're going to essentially print the template that you want, and of course there could be some self-assembly involved with this as well. This is the step flash imprint lithography process that was developed, and again we're running out of time, so I'm just going to show you that the idea is, though, we don't have essentially the creation of the image using something like UV to do it. It avoids that, and so there is a cure step, but not to create the size of the image. And so people are working on this as kind of the next frontier to create, essentially shapes like this. And there is actually an NSF Engineering Research Center called NASCENT, which is also at the University of Texas. And the focus here is, okay, what are the new devices we need to make, like flexible devices or wearable devices, and so on. And of course, lots of new sensors that people want to make now. The Internet of Things is driving a whole lot of interest in how we come up with lots of cheap sensors. And so, combining nanoscience with societal needs, essentially, here are the kind of things that are working on. I might mention that right now, there's no control people working in the center, in spite of my complaints to the PI. But he says, we really need metrology in order to do control, and he's absolutely right. So again, if people can develop metrology, new ways of measuring the dimensions and the shapes and so on, then that would be good. So again, just quickly, another commercial for NASCENT. So, and here, by the way, RtR stands for roll to roll. So now they're talking about, you see that middle figure, the kind of device now they're using. So it is continuous processing now is sort of the goal, how we get from the batch type of operation. So what are the long-term trends? I think, as I said, that we need more sensors, new sensors for nano manufacturing. The wafer design technology is going through radical changes. People say, well, we used to be able to predict 5, 6 years out. Now we can't predict more than a couple of years out where things are going to be in the future. And things like three-dimensional chips are part of that as a way of cramming more capability onto the fixed space that you have. I think fault detection, because a lot of the control technology is mature, that is really, I think, an area that's ripe for contributions. Industry consolidation is happening, and so the company you thought you were working with 5 years ago is now a different company, or it's been combined with another one. And really we're down to like 4 big companies that make chips: Samsung, Intel, and TSMC being three of the big ones. Like I said, the flexible electronics are going to really come into play here. And then finally, I think some people are now dreaming about photonics. And so if someone is looking about, what should I be working on 10 years from now, that might be an area that would be worth working on. So in conclusion, I think Clearly, we face insurmountable opportunities. So there's lots to be done here. I've had the benefit of working with a lot of really smart people, bright students, and you can see a whole lot of them, went from doing, research, PhD level research on control into the semiconductor industry, and that's had a big impact. And then finally, I should acknowledge a lot of the sponsors that we've had, that basically we work the student would typically be on co-op assignment working with the company, come back to UT again. So we had a really good system for doing this. So that's been, I think, a great benefit. So with that, thank you for your attention, and I'll be glad to have time for a few questions maybe.
Yeah, thank you.